Hello.
Hello.
Hi.
Hi. Can you hear me? Yeah.
Yeah, I can hear you. Yeah.
Cool. Sounds good. Um. So, can you like briefly tell me about yourself so that I can adjust my interview?
Yeah. So I am just getting back into coding. I was a software engineer, a full stack engineer, about 2 years ago, and then I stopped to move on to do, I moved to a different opportunity that didn't involve anything technical or coding.
Mm-hmm.
And now I'm trying to get back into it, and yeah, and so I have some interviews set up for, in the following week, in the coming week, I have a few interviews that I'm, prepping for, and I've done one of these practice interviews, and I'm hoping on doing a bunch more. And I also just picked up Python as a language kind of like last week, and I'm trying to, learn that for whiteboarding, just because I know it's less verbose. I was doing Java
Mm-hmm.
mostly. And it was also years ago. And so, I was thought, why not just start from scratch and start with a language that will be better for the interview process? And so I'm using Python right now. And yeah, are you familiar with Python?
Yes. Yeah.
Okay.
I mean, I don't code that much in Python, but yeah, I can understand.
Okay. Just because I might have syntax questions and stuff as I do this.
Okay. Sure. No problem. Sure. So, do you want to do like a medium, easy, or a hard problem?
I, I mean, I don't want to do an easy one.
Okay.
Uh,
Yeah. Makes
I'd
sense.
be interested in, I mean, if you have a hard problem that's interesting, I'm happy at failing at it, but like trying to work through it if you want to try that. But
Okay.
if I can make some progress on the problem, that would be,
Yeah.
yeah,
Okay.
whatever,
Sure.
whatever you think. You pick whichever problem you think. Yeah.
Okay, sure. I guess like we'll start with medium, and if you solve it quickly, we'll move on to like if you think you can do it pretty easily or quickly, then we can move on to a hard problem.
Yeah,
Sounds good?
that sounds good. And it will take me a while to code anyway because I'm new to Python. So maybe we should just do the easy anyway. Yeah. Yeah.
Okay, sure. So like if we are given a binary tree, right?
Oh,
So
sorry. Can I ask one other question?
yeah, sure.
Yeah. Are you do you like actively interview at your company, and can you just give me like a 10-second overview of what your background is? And
Sure. Yeah. So at my company, I used to work for Amazon, but now I'm working for another startup within Walmart, and I actively interview like I've done like maybe like 30, 40 interviews in total, and I've also done like maybe like 20 or 10 to 15 interviews even on this website as well.
okay.
Um, yeah, and I've been working in software for like maybe like 10 years, yeah, minimum.
Okay. Yeah, that's a lot. Yeah, I was only working as a software engineer for like a year and a half.
Uh-huh.
I'm fairly new to all of this, and that was years ago anyway. So yeah, but yeah,
Okay,
let's get started. Yeah.
okay, just give me 1 minute. I'll just close the door. 1 second.
Okay.
Okay, cool. So if you are given a tree, right? Let's use A, B, C, D, E, F, G, H, I, J, K, L, M, N, O. Right, so this is a tree.
Yeah,
Let me adjust it so that it looks somewhat tree-like.
yeah, I get it, but yeah,
You get it
yeah,
right.
that looks good.
So
All
yeah,
right.
so the bottom ones are like two. Every two child goes to one above, right? So D, H and I are children of D, and J, K is child of E. F is child like this. Yeah, makes sense.
Yeah, that makes sense.
Okay.
Can you give me 30 seconds? Sorry, hold on.
What did you ask? Sorry.
Sorry, can you just give me 30 seconds? I just need to hold on.
Sure, sure. Yeah.
Yeah. Can you close the door, please? Can you close the door all the way, please? Okay. Sorry about that. Okay.
Yeah, no
Okay, so
problem.
we have a tree. Yeah, we have a tree. Yeah, and each
And
node has children. Yeah.
yeah, each node has two children, and you can. And this is not a balanced tree. And by balanced
Oh, it's
tree, I
not.
mean like
Okay.
yeah. So it can be that there might be like few missing nodes here,
Okay.
like this, right?
The depth of the right and left node are not necessarily the same.
Yeah. Uh-huh.
For this. Right. Okay.
So yeah, so it can be like this, and the output I expect here is A, B, D, right? H, because we are going along the boundary, and we want to go
Yeah.
along the boundary from left, then to the bottom, then all the way to the right. So that's why the output is A, B, D, H, I, J, K, N, O, right? And I've just put dots,
Yeah.
type everything, and then after O we have G and comma C. Does it make sense?
Yeah, that makes sense. Yeah.
So this is
Um,
boundary traversal output, right?
yeah. Yeah.
So you'll be given
Um,
like the node of the tree, root node, and then you're asked to print like collect all the um, node values at the boundary. Yeah,
okay.
in a
Yeah.
anti.
Yeah,
Hmm. What were you
that
asking?
makes sense.
Okay.
No, my initial instinct is just to do sort of a breadth first
Uh-huh.
traversal of the tree. And, as you're doing the breadth first traversal of the tree, the first and last nodes that you collect at a given level in the tree are going to be, you can collect them as like in a couple separate like arrays, and then you can just take that bottom level, and you can tack on the initial portion, which would be ABD, and reverse the last portion GCA and tack it on at the end. That's what I'm thinking. So you do a breadth first thing. You have so you have a whatever, a queue.
Hmm.
Normally, what I guess you use for breadth first. I guess for depth first, you generally use stack. For these queues, you pop it out, you put in, you try in the, like, let's say we have three different, or we have like, I can just write for the first leg of the triangle, I guess, and an array for the last leg of the triangle. And equals this, and then you have a, let's say like BFS, first search queue, which will be this, and you can just use an array implementation of this or on implementation, whatever. And you push in the top node and you say A, okay. And you put that into the first leg here, and then you pop this out and you put in B and C as its children. And I guess you might need to keep track of the level that you're at because you want to know. So maybe you create like this character at the end here, which would like some none type or character at the end to mark that you're at the end of a given level. And so at this point, you would pop pop none and A off, put B, C, whatever, none at the end. This is not completely formal at this point, obviously. And you would put B in, this is first leg, this line. Put first B there, and you would put C here. And then you would continue along with this, pushing, and then let's see, A, B, D. For the next one, it would end up being B and G here. And at the final level here of the breadth first, you would have I, J, K, N, O, and then you would just say, okay, return. I think that you can just, I don't know how you concatenate arrays in Python.
What are you asking? What to do? What? Can you hear me?
Hello?
Yeah.
Can you hear me?
Yes. Yes. So
Okay.
you were asking how to
Uh,
do.
I mean, this is pseudocode anyway, so I can figure out how to concatenate, and then like reversed of last leg,
Hmm.
something
So so
along those lines.
uh-huh.
Yeah.
So you're saying you would do one BFS traversal of the whole tree, and how do you know when to add elements you visit to the first leg and when to add it to the last leg, and when to add
So
it to.
yeah. So first of all, you would add a to
Hmm.
the queue. You'd be like,
Okay.
okay, so there's nothing at this level, so we're going to put none in here, or maybe we'll put none here or something. I forget. I feel like I've done this at some point. And you pop,
Uh-huh.
and then as you pop off the elements in here, once you get to
Hmm.
none, you
Hmm.
know that you've, uh, yeah, you pop off because, um, oh no, never mind. Because you're not popping off. You're taking from it's a queue, so it's first in, first out. So I guess I need to use not some. I guess I can use I think there's DQ, which is this uh, Python queue implementation, which I could
Okay.
use for that. You would do a and then none or some marker character here to mark the
Hmm.
end. And a in this case, it's a special case because it's in the first leg and the last leg, but we're just going to consider this based on your example here. We're just going to include this in the first leg. So we're going to just seed this first leg with a at the beginning, and then we're going to uh, we're going to take a off the front of this because it was we're going to continually just take off the first part of the array, and then we're going to put its children at the end.
Hmm.
And we're going to b and c here, right?
Okay. Hmm.
And we're going to see, okay, we see that this character means that we're at the next level. So we're going to pop that off, and now we're going to say, okay, we're at the next level. So we increment some, or we say the character following that, b in this case,
Okay.
is going to be added to the first leg. And so I guess you kind of need to, so B would be the first leg. And sorry, when we would do this, whenever we consume that character, we'll put it right at the end of the current level. And so we'll
Okay.
consume B, and we'll put at the end, we'll append D and E at the end here. And then C, how do we know to put it in the last leg? We'll keep track of it. We'll keep track of like a single element. And then if we hit this, like we'll keep track of some sort of previous element um, uh, variable. And then if we hit a marker for the end of our level, then we'll add that previous element to this last leg list. And when we consume that, again, we put this at the end, or sorry, we
Hmm.
put the C, the FG first, and then we put that character at the end, and that's how we keep track of levels. We keep track of the previous element.
Hmm.
And then by the end, we'll just have a populated list of first leg and last leg, and then we'll just, concatenate the three arrays
Uh,
like that. Does that?
Sounds good to me. And what about like the case where we have F, right? Because um, we also have F in the output. So HIJKF and then NO, right? So because F is
Oh,
at,
sorry.
yeah,
Yeah, I did not. I didn't. I guess I ignored the F. I thought it was just A B D H I J K N O. I didn't see the F. That is an
yeah,
oversight. Yeah. Um. Okay.
because F
Let's
is
see.
also part
So
of the boundary. So that's why we want to include it.
right. So maybe what I could do instead of doing, interesting. So how do I do this and keep track? Maybe I'm thinking a depth first search sort of would work better for this actually.
Okay.
Let me think. Because if I do let's see, a pre-order like traversal where let's see, I can just populate this list. Let me see. Interesting. oh, A, B, D, H, all the way down, put that in a list. If I hit a leaf, so I'm going to hit these leaves in sequence if I do a certain depth first search. So I can do A, B, D. Okay, so I think it's a fairly simple. It's fairly simple to just get the. I can do this in separate. I'm trying to think about how to combine this into one function, but it's easy to just get the leaf nodes in order. I can just do a depth first search, which will hit I first, and then it'll hit J, and then it'll recurse up back to B, which will then go down to E and J, and then K, and then it'll go all the way back up to A, which will then examine its right node, which will go to F, and then go. So that should get those in order. That's like a simple depth first search, which just checks if a given node is a leaf, and then appends it to some global list that we're looking at. And then, I separately just kind of traverse the boundary. Yeah, I can just separately kind of traverse the boundary.
You mean left and right boundary?
The left and right boundary. Because I think it would be honestly better to do that than introducing some complicated logic or some logic into the actual function to check. I feel like it might be more complicated to check actually whether or not we're on the left or right leg. We could just do that kind of separately, and it would be the same time complexity. Yeah. So maybe I'll just do that. Sorry about going down this route. I didn't see the F. I thought that was omitted from the. I thought it was just doing like the triangular sort of like outline of this whole thing. But okay.
And that's fine. Yeah.
Okay. So do you mind if I start coding?
So what is your strategy for the bottom one? You said you would use DFS, and then for the left and right, what would you use?
Again, I would just use I would use a DFS. I would just keep traversing just as left or as right as I possibly can. Yeah, that's it. So I would just keep on taking the right node because I think, sorry, can I ask, because we need to look at a couple different edge cases here. So if this were, that might not work. If this were NO here, right?
Yeah.
Okay, let me think. So this would just still be, this would be A, B, D, H, I, J, K, N, O, and then G, C, A?
Yeah.
It would be, okay. Let's see. Let me just take these away. Let's do something like this. Just make it so. Okay, so this would be A, B, D, H, I, K, G, C, A again?
This would
or
be
not
A,
G, C, A,
B,
just
D, H, I, K, F, G, C, A. Because think of it like a rubber band around this tree, like a tight rubber band, which bends around the corners.
Oh.
And you only print like so. For even rubber band, I think is a bad example. I would say like anything which is like a leaf node and outside, right, which doesn't have any not even that. How to describe it? So let's say like if you look at the left side, right, those are all part of the boundary, right? And I think left and right are pretty simple to reason about, right? Like what is a boundary? For the left side, it is ABDH. For the right side, it is ACG. And for the bottom side, it is a little tricky because of these cases, right? Where you can have one child or no child because it is not balanced. So in this case, you'll have H, I, K, F, right? And then G.
Oh, and then G. So sorry, I thought you said FC before, and that confused me a little bit. So okay. So then I think my algorithm still works because I can separately just examine the left and right leg, or the first and last leg, left and right leg, or whatever, of the tree, and that will get me back. And then I just need to do a depth first search to get each of the nodes in order, and that should get me there. I think I can't think of edge cases where that wouldn't get me there I'm trying to think of, yeah, let me just try it. Let me try it out. I think that should work.
Okay.
So let's see. So let's define a function here, which is going to say print boundary or something, or just boundary, which is going to take in. So what is the input to this function?
Node of the tree, root node.
Oh, it's just a root node. Okay.
Okay.
So, and it's a root node, and that, like, should I define a class here for node, or should I just assume that there's an implementation?
For now, you can assume that, and then you can write it later if we have time. Yeah.
Okay, so we have a node here, and we want to, let's see. Yeah, we wanted first process. We just want to check if this node. So if node dot left, if this is a not node dot left and not node dot right, like these leaf nodes will have, yeah, this should work, I think. Basically, let's say, I mean, I guess we could define this boundary. We can define a like output array output, or let's say boundary. We do this print boundary. Boundary is going to be an array that we're just populating here, equals this array. And if we get to a point, and we're going to define this function, which is going to be DFS in here. We're just going to take a node, and we're going to check if, let's see, I don't need those for Python, I don't think. So if node.left and not node.right, so if it doesn't have any children, then I want to just append it to my boundary. So boundary dot append node. So if this is a leaf node, then I want to append it to the boundary. Cool. And if it's, let's do this. I don't think it likes this. Yeah, okay.
And by boundary array, do you mean by boundary array, do you mean like the overall boundary, or just like the bottom or the right or the left boundary? Or?
Well, yeah, I'm first. This is going to be the, I guess I was going to, this is just the bottom boundary. So I guess I can do
Okay.
floor boundary or something.
Okay, cool.
Yeah, and then, you know, else we can examine, we want to first examine its left node, and then we want to go to its right node. So we want to call DFS. You know, let's see, you know, let's actually do this. Let's do LF not node dot left, and we're going to do something here, or we can just do LF node dot left, and we want to do DFS on node dot left. LF, why do, no, you know what? I'm not going to do this. I'm just going to say if node dot left, do that. If node dot right, then we just called this on node dot right, DFS node right, and we want to boundary dot append. We want to return here. It doesn't matter what the return value is. Let's see. So if we're saying if there is no node dot, if there's no left node and no right node associated with this node, then we want to append this node. We know we're at a leaf node. We want to append this node to our boundary list or for boundary, and we want to return. Cool. I guess I don't even need this. Whatever. Actually don't even need a return value in here because I guess there's default return. Cool. So if node.left, then we call DFS on node.left. Oh yeah, sorry about that. So, boundary, floor boundary. So here, floor boundary dot append node. If node dot left, then we do that. If node dot right, we do that. Yeah. So I feel like this is simple enough. I feel like this should give us our floor boundary. And then we want to, let's see, you want to define, right?
So because
Does
you
this
have
make sense?
yeah, this makes sense. So because you have completed print boundary, right, for floor boundary, can you like run through an example? Like, can you test it out?
Yeah. Do you want me to do you want me to just like write out, or let's take an example that we wrote down below.
Uh,
Let's do this right here. Let's just take a look at this. So in this case, we would get a node would come in here. We would say, oh, sorry, we need to call DFS, the node itself here. And we're going to say, okay, yeah, so DFS gets the node, if not node.left, so node.left, or left and right are properties on this node. If it doesn't have node.left and it doesn't have node.right, then we're going to call floor boundary and append this node. We don't want to append it to our floor boundary, that's good. So if node.left, in this case, node.left is B, which is good, it does have node.left. And then we call DFS on node.left, which is then the B node is passed into here, which is going to go through the same thing. It has a left and a right node. Cool. Let's see. Yeah. And then it will check its left node. It'll say DFS node.left, in which case that's this D here. D is going to do the same check. It's going to do node.left, DFS node.left, which is going to be H, which is going to say, okay, H in this case, if it doesn't have left and right, which it doesn't in this case, we're going to floor boundary that append this node, good. And then we're going to, we're going to check these, even though we don't have to, we can just put a return statement in here.
Okay.
And return up to D, which is then going to return up to here to line 13, which is then going to check its node.right, which is going to call DFS on its node.right, which is also a leaf node. So that's going to append I to there, which is then going to return, which the function call for the D node is then going to return after all of this. And we go back up to B, which now we're up at line 13 for B again. And we're going down to its right node in this case, and E. And so E, if not node.left and not node.right, no, because it has a node.right.
Okay.
So yeah,
do you see
it has a node.right.
Do you see a bug around like on line 10?
Or boundary dot append node dot. Do you mean node dot value is what we want, or?
Yeah.
Okay, just yeah. Yeah, we don't. I was a little bit confused about if you wanted the values in the output array or the nodes themselves, but I guess we can just do value here. Yeah. Yeah. Yeah.
You start with the other one, the left one or the right one.
Yeah, so at E, we go down to node.left, where it doesn't have node.left in this case, so we go to node.right. We call DFS on node.right.
Oh, no, I mean, like,
then it's.
I mean, we are good with this example. You can start with the other function.
Oh, okay. Okay. Cool. So let's see. So we call DFS on node here. That's fine. And then we want to do a couple more things. We're going to define like right boundary, which is going to take a node and return something. We're also going to define left boundary, left boundary, which is going to take a node, and it's also going to do something in here. Each of these is going to have a separate array. I guess we could just, we shouldn't be tacking onto, I guess we could do these in order, where we do the right boundary first, and just have boundary and just append to this boundary here, which would be fine, I guess. But let me just do it. Let me do it this way first, and then I can That's not that much of an optimization. Okay, right. Okay, so print, sorry. Oh, DFS, oh, let's do, not this, let's do DFS right, DFS, whoops, left, and we're gonna have two similar things here for each of these. And it's just gonna be, let's do left boundary left first, and then we'll do right. Okay, so we have this in place, and for this, we're going to check. We're going to do something similar in here. Let's see. To do something similar, we're going to say if not, or if we're just going to say if node dot left. Oh, so I'm confused. Oh, sorry. Yeah, so this might not work. I might have to do a combination of depth first and breadth first, I guess, which kind of sounds annoying. But now I'm thinking you could have a tree where you go A and then B, and then maybe D is omitted here, right?
Okay.
Right, and so you have this and this. In which case, what would the output be for this?
It'll be A, B, E, K, F, G, C, A. F, G, C. Yeah.
Oh, it would be E. So E would be included in it.
Yeah.
Yeah.
Because it is part.
Okay.
Yeah.
So what I need to do is I need to do a combination depth first and breadth first. So the depth first thing happened there, and the breadth first I need to use the code that I was doing before to get the beginning and end of a given level of the tree. Does that make sense?
I mean, why do you have to use both? Like, like, can you give me an example there? Like, why would you use both?
Let me think. So, I guess we can just do. I guess we can just keep on prioritizing going down the left part of the tree, and then if we don't go down the left part of the tree, we go down the right, and we keep on trying to go left, but we go right, and I think we'll actually maintain being at the left boundary of the tree. So we can do that, I guess. So maybe I won't use the breadth first. So left boundary equals DFS left of node. We're going to first check if there's no dot left. I guess now I'm a little confused. If I get to, what if I had B and then another A, B, C here?
So I guess you were on the right track, right? Like if you see a left, you prioritize that. Otherwise, you go to the right.
Yeah.
If there is.
I'm just trying to think of just maybe another edge case that I'm not thinking about, which is, let's say we had this, which is A, B, C. Let's just put whatever J in here. It doesn't. Whatever. And this and J. So in this case, the left side of the tree so the boundary in here is going to be A, B, C, K, J, L, F, G, C.
Yeah.
Okay, because then it, yeah, so we can just prioritize going to the left for the left boundary. If we have to go to the right, then we go to the right, and we append the values as we see them. If we can go left and go right, this is the problem. How do we know not to? So if we go to B and then we go to C, which is prioritizing going to the left, we append C to our left boundary, and then we go back up to B and then go to E. I guess we then, if we're going to the right.
But why are you going back up? Why do you have to go back up? Right? Like you're going left, and then if you don't see anything on the left, then you can just go further down, right, by going to the right.
Right. I'm saying I'm going ABC down to this level at C. In which case this doesn't have children. This is just.
You're saying this read children?
Yeah.
Okay. So in that case, K wouldn't be printed.
Oh, okay, yeah, it was more. Okay, good. Never mind. I thought.
Yeah.
Yeah, we need to space these out a little bit more, maybe. Here, like that is what I was thinking.
Okay. Yeah.
In this case, sorry, just to be clear, in this case, it would be A, B, C, J, L, F, G, C.
Yep. Uh-huh.
Okay, it wouldn't be K wouldn't be involved in the left boundary.
Yeah, because you already printed its child, so yeah, which is J. So
Okay.
that is not part of because your J is part of the boundary, right? If there was no J, then maybe K, but there is J.
I mean, it just like visually, yeah, it just visually looks like it could be included in the boundary if you were drawing like, if you were just drawing the boundary around a tight boundary around the whole tree. That's why I was thinking that, but
yeah, I think that is like a confusing metaphor. You can ignore that.
Okay. So I'll just assume you go left, and if you don't go left, you go right, and that's fine.
Okay. Yeah.
Let's see. Yeah. So if node.left in this case, then you want to, well, first when you hit a node, you left boundary dot append node dot value in this case. Okay, and then if node.left, you will call DFS left node dot left, and if node.right, DFS left of node dot right, because that's ensured to be the left boundary because we have no left of its parent. So we go down to that. We then, okay, so in this case, we have A, B, and we only want A, B, C in this case. So we go A is at the top. We say left boundary dot append node dot value, which is A. We check if it has a left node, in which case it does. And so we call DFS on its left. And if we call it on its left, we don't want to then call it on its right. We only want to call it on its right if, if we don't see anything on its left. I guess we could just do elif node.right. So if node.left, then we call DFS on its left, in which case B would come in here. It would be appended, B would be appended to the left boundary. We would check its left again, which would be C, which is good. We would call DFS left on C. We would check if it has, we would append C to our left boundary, good. If it has a node.left, which it doesn't. If it has a node.right, it doesn't. And then we return up the tree, and that's fine. And we've printed out the left boundary. Does that work if we have, let's just eliminate C for a second. And we would want, so in this case, we would want A, B, E, K, J, L, F, G, C, right? Excuse me? Hello?
Oh, sorry. I think I was on mute. A, B, E, K. Yes.
Hello?
Hello. Can you hear me?
Yeah, you cut out for a little bit. Yeah.
Oh, okay. Sorry. Yeah. A, B, E, K. Yeah. Looks good. A, B, E, K, J, L, F.
Hi, can you hear me?
Yeah. I think there is some weird problem. Can you hear me now?
Yeah, I can hear you. Yeah.
Okay. So I was saying, yeah, A, B, E, K, J, L, F, G, C. Looks
A,
good.
B,
Yeah.
A, B, E, K, J, L, F, G, C. Okay, so in this case, we would have A, which would come in. Node.left is B. Good. We would go to node.left. Good. Node B does not have a left node. We would go to node.right, which then would be E, which would be, we would append E to the left boundary, which would then we would look at its left node, which is K in this case. Great. And then, oh, so I guess we don't want to. We're going to double up on a couple nodes, so we would just want to check if it's a leaf node in this case, which is going to be this same check here.
Okay.
Yeah. So there, because we don't want to double up on the leaf, we're capturing that in our DFS. Right boundaries would be pretty similar to this. I know that we could do this with more conditional logic, like add a parameter. We could do one boundary, one left and right boundary function, and then have a parameter which will, dictate right or left but I'm going to do this to make it simple for me right now. If no dot left and no dot right, we return, and then we want to replace this here. Good. Dot append no dot value, and then we're just going to switch these up, right, 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 and left. Oh, sorry, right DFS right on these, and DFS left for these, and then return. And then at the end, we want to return left boundary plus lower boundary plus reverse of, and I guess we don't even need to reverse because we could do a post. We could do a post order. We could add this post order in this case, which would give us the reverse list, I think. So we could do something like this. So then we would just do right boundary. And I think that might work.
So you're only adding node after you're recursing, right? Okay.
Yeah, for the right boundary. And then I'm doing a pre-order traversal for the left boundary and a post order for the right boundary, and then I'm just doing a leaf check for the DFS function up here. So, yeah.
Okay.
Does that make sense?
Makes sense. Do you see overlap somewhere?
Yeah.
Probably overlap where you might be printing a node twice.
Oh, overlap in terms of the output of the function might be returning. So the only overlap that I thought was if it's a leaf node, because on the left and right boundary we're sometimes because G is going to be, in this case, G is going to be included in the floor boundary, and so we don't want it also included in the right boundary. So we kind of omitted that by checking if it's a leaf node here.
But there's one more.
The first node. We don't want A in the final. So I'm going to return this, or I'm going to do this, and I'm going to pop off the last element. I'm going to say this result equals this result dot pop, and there you go, result.
Okay, cool. Okay, looks good to me overall. Okay. What do you think is like the time complexity and space complexity for this one?
How are we defining the input size? Are we defining it as the number of nodes in the tree?
Yeah.
Well, then it's linear in the size of the tree, in that we need to examine each node, because I don't know a better way of getting the floor boundary besides doing like a full DFS search on the tree. So it's linear in the size of the nodes, in the number of nodes in the tree. And then the adding on the DFS left and right are just kind of minimal in terms of the full traversal of the tree. So it's linear in the size of the tree.
And what about like the space space complexity? So that is the time complexity.
Yeah, the space complexity, I guess, would be log base 2 of n, given that we have a stack of our call stack can at most get to the max depth of the tree. And the max depth of the tree, I guess the max depth of the tree, I guess we said this isn't balanced. So we could have, actually it's going to be linear. It's not going to be log base 2, because the worst case situation for this tree is that we have a linked list, and so, and so it would be a linked list. It would be traversing a linked list and having to keep track of the entire linked list in terms of, having a call stack that is the length of the linked list. And so, linear for time and linear for space is what I'm thinking.
Okay, and I think you have already like covered all the cases, but if like somebody asked you like how would you like unit test this, what would you do in that scenario?
How would I unit test it? I was thinking, how would I unit test? I would just try to capture all the edge cases. I've written, I would just try to capture all of the potential edge cases, and then I would also have a unit test that would, generate random binary trees and see that it, but I haven't thought that much about it. Yeah.
Yeah. Basically, like you would come up with all the various edge cases you can think of, construct those trees, compare them with your expected output.
Yeah.
Yeah. Okay. So,
Question. So, do you mind? Can we? I feel like can we move on to the? Can we maybe talk about the harder problem because we have 15 minutes?
Yeah, sure.
Okay.
So
Also, sorry about the misunderstanding. It's a
no,
little confusing. The problem's a little confusing.
yeah, it is. And I think I gave you a bad analogy where
Rubber band. Yeah.
and yeah,
Yeah.
so let's say we have like have you heard of this problem, like a rod cutting problem?
Is this just yeah, I probably have heard something. I mean, I would like to, let's talk about it. Yeah.
Okay, so you're given like a rod of length is equal to 5, and you're given prices of different lengths, right? So let's say length 1 is equal to $2, length 2 is equal to maybe like 3, length 3 is $1, length 4 is maybe 5, length 5 is equal to maybe 4, right? So if you're given all the lengths and all their prices, what kind of combination would you cut the rod so that you can sell it for the maximum price overall, right? So you can cut the rod in this scenario, like you can cut it by just using rod of length 1. So if you just have your cuts with rod of length 1, you can accomplish total length of 5 by 1 plus 1 plus 1 plus 1, which will give you the total price as 10, right? And then if you do 2 plus 2 plus 1, that will give you a total price of 6 plus 2, which is 8. So what particular, like, what is the maximum price you can get from this rod by cutting it in a certain configuration, right? Of all the possible configurations.
So what I'm thinking is that it's a pretty simple dynamic programming problem, where I'm just going to it's going to be linear time complexity, in that I'm just going to recurse and say, okay, let's say we have our prices here. So we have, I guess this is like a dictionary that we're given of prices. So I'm going to say like rod length here, and we're going to give like a prices dictionary in here, right?
Okay.
And then I'm going to loop through the individual prices of the rod, and I'm going to recurse and say, let's just do this in pseudocode. So I was going to loop through and say, and for each price in the dictionary, I'm going to keep track of that price, and then I'm going to recurse and say I want to find the maximum of the rod minus that length that I'm currently at, plus the price that I would get for that length. And then I would also keep track of, I would just memorize, so I would only ever have to catch one of my subproblems once. So I would have this memoization, which is going to have as key values rod lengths and prices. So prices here as values, and the prices would be the max price that you can get for a given rod, given the dictionary of prices that was given the problem. And so I guess I can even write this up. Maybe I'll just write this up. So let's say we have this memoized cache here, and we have this here, and we want to say for price and prices. I think you can loop through the keys in a dictionary like that, right?
Yeah.
Okay. Well,
I don't know. At least in JavaScript you can.
Okay. I'm gonna check if if rod length is in if rod length in memo, then we just want to return that rod length, and then for price and prices, we want to get the max of, so let's see, what we want to do is we want to keep track of a max here. Let's say max price. I could make this more elegant in Python, but I'm not that familiar with Python right now, so I'm going to do this pretty simply. So max price is, let's say 0 in this case, because I don't need negative prices for, yeah, it's always going to be positive prices. So for price and prices, we're going to say max price equals max, or math.max maybe. I don't know. We can pick. Oh, max is a keyword. It's lighting up. Okay, so max of max price, and let's see. We want cut rod of rod length. Oh no, we're not going through the prices. We're going through the rod lengths. So for lengths in rod length. Oh no, sorry, prices. This is confusing. So for lengths in prices, because it's the length that we're getting as the keys in here, we're going to do for length in prices, we're going to do cut rod of length. It's not pretty right now, and I guess we can pass down prices, but we don't need to. Yeah, so let's say, yeah, let's imagine, can we just imagine that prices was just global here, or I could just write a wrapper function around here. So prices just exists out here, and then we have this, and I would put this all in like I could do a wrapper function, which is like, whatever. Wrapper of rod length and prices here, and then we have this memo, we have this prices, which is already here in the scope. We define cut rod here, and cut rod just takes the rod length because we have this prices in scope here, and we have this memo cache in scope here. We check if rod length is in memo. If it is, then we would return prices of rod length. Max price equals 0. For length in prices, we want to say max price equals max price. So we want to say the current max price, and we want cut rod of length minus for length, rod length minus length, rod length minus length, and plus, let me expand this. I guess I have 7 minutes. Okay. Cut rod of rod length minus length plus prices is the dictionary that we call. Okay, prices of length, of rod length, length. Sorry. And then we want to return max price. We also have a base case that we haven't hit here, which is if rod length is 0 equals 0, we want to return 0. And sorry, max price is this, and we want to add max price to our cache. So we want to say memo of rod length equals max, something along those lines. Does this make sense? And then in here, in the wrapper function, we want to return cut rod of rod length.
So you are basically like picking up a particular price, and then you are deducting the length for that price and recursing on that. And then you're keeping track of the max price.
Yeah.
And it's memoizing. 1 second, let me check the memoization. Memo problem.
Oh, sorry, memo. Sorry, this is what I wanted.
Yeah. So, but will the memo be just have a key of a particular rod length for a
Yeah.
given? Uh-huh.
Yeah, so for a given rod length, the return value for that is going to be the only time that it gets put in the cache is after examining its possible, examining all possible, sub problems underneath, you know. So we're gonna for each thing, we're always gonna call. So this cut rod function is only going to be called once for each rod length because we're saving the results of our past function calls on that. And yeah, for each rod length, there is going to be a maximum dollar value that you can get from that given rod length. Yeah. Oh, sorry. There's something. Sorry. There's a problem, and there's another. Sorry. If rod length is less than 0, then I want to return like infinity or something, math.infinity, because I
But
don't.
will it go less than 0?
Yeah, I'm thinking if it gets down to a point. Oh no, yeah, it will. It will, because it'll get down to a point where maybe my rod length parameter here is 2, but it'll go through the prices in here, the rod lengths in here, and it'll subtract 5. It'll say in here, rod length is 2 minus length, which is 5, so we're going to get -3 as our function. And when we return that function call, we don't want to incorporate that into our max price calculation here, because that's not a valid solution. Yeah.
Okay. So in that case, you would return like negative infinity, right?
Oh, yeah, that's what I meant to do.
Okay. Cool. Looks good. I think we have like 4 minutes. You did pretty well, I think, like for both the problems. Do you want any feedback?
Yeah, I would just so the time. Let me just say that the time and space complexity, it's linear for time complexity for this. And again, it's going to be.
It wouldn't be. I was saying like it wouldn't be linear, right? Because you're comparing all the different possibilities here.
Oh, sorry. Because in each of these but so it's going to be O of n times m. Oh, so O of n times m, where n is the rod length, and then m is the number of prices the number of rod lengths in our prices dictionary.
Yep.
Yeah. And then it's going to be it looks like linear space complexity, because all we're dealing with is the call stack. So it should be the call stack at maximum is going to get the length of the rod if we just consecutively take one unit length off the rod. So the first call, essentially, the first traversal down the left boundary is going to be the longest, and we're going to
Okay.
Yeah.
Sounds good to me. Other than that, like everything looked good to me. Only like minor suggestion would be like you should talk about like some kind of unit testing, and you should like volunteer to provide like space complexity and time complexity, so that like the interviewer doesn't have to ask you for it. That gives you like a minor like a sort of like a brownie point, because you provided it on your own. Other than that, other than that, you were walking through all the problems as you solved them, so that was a good thing, and you were able to solve the problem pretty well, both of them. And it didn't look like maybe like the print boundary one, there were like some edge cases, and you discovered them on your own as well. So overall, it was very good. Yeah.
Okay. Good. So I also have a question. Are there any, so I'm just getting started doing this preparation stuff. Are there any resources that you would point to as like great resources?
Everybody like goes through lead code and cracking the code interview. And if you had to warm up on like your algorithms, just in case, if you want to, I don't think you need to, but if you want to, there is a good course in Coursera by Robert Sedgwick, and that is for algorithms. And then there is one more. You must have heard grokking the system design interview for design interviews.
Yeah, I had that sent to me by the past. So I've done another one of these interviews, and the other guy also sent that to me. But I don't know if, I guess I only have like a 1.5 year experience And so
Uh-huh.
I've been talking with people, and I haven't been doing this for 2 years anyway, so I'm just getting back into this. And so I may be applying for positions, or I am applying for positions that I don't think that I'll be getting many system design interviews because I'm
Uh-huh.
not going to get like a senior or yeah.
Yeah, but most of the interviews they'll have like any big tech will have at least like one system design, right?
Even for
So
even for
yeah,
relatively junior positions.
yeah, for
Okay.
any big tech you'll have even with Amazon I think you have like at least one system design. Sometimes they skip it, but most of the times you have it. So you might
Okay.
as well like prepare for it just to be on the safe side.
Okay.
And these two resources are great. Like whenever you have time, I think you should go through them. That will help
Okay.
you a lot.
Okay. Sounds great. Yeah.
Yeah, cool. All the
And
best.
then yeah, you'll give some written feedback too, right? If you yeah.
Yeah.
Okay.
I don't know what I like. You did pretty well, so I don't have much feedback, anyways. Like only thing
Okay.
I would say, like I mentioned, was like volunteer to provide as much information. Like also discuss like if you have various approaches to a problem, and you don't have time to code everything, so you might as well just like mention like I could have done it this way, but I did not do it this way because of so and so trade-off, right?
Yeah. Yeah.
So that yeah. So and if you have like try to solve the problem like quickly so that you can solve more problems like you did today, right? So that if they are comparing you with other candidates and if you did solve more problems than them, then obviously you uh, have a better chance at cracking the interview, right?
Okay. Okay. Perfect. Um,
Cool.
yeah. Thank you so much.
Yeah. Have a good day.
You too.
Bye.
Thank you.